So, what we have seen in the last few classes is filters that are used on the AC side. So, essentially to minimize the harmonics in the currents drawn from the AC system, and we also saw the design of one type of filter which is a single tune filter. Okay. So, there are other filters which are used in a DC transmission system. For example, on the DC side, we use DC filters, and there is also, in addition to that, there is a smoothing reactor. So, there is a large inductance which is connected in series in order to minimize the harmonics in the current on the DC side. Now, this is presence of smoothing reactor is one of the reasons for having the model of the DC side as a current source. See, if you recall, one of the models is just a current source, a constant current source on the DC side. Now, that is because of the presence of a large inductance which is called smoothing reactance. So, I will not get into the details of the smoothing reactor or the other DC filter, but one point to notice, if I have only back-to-back connection or back-to-back links, if I have back-to-back links, that means we need to interconnect two systems without having a transmission line. That means the rectifier and the inverter are in the same building. Okay, so there is no transmission line. Such DC systems are called back-to-back links. So, in this does not require DC filter. DC filters are not required. So, that is about filter. We will briefly look at one more equipment that is required in a DC transmission system. We saw that the reactive power is actually absorbed by the converter. Okay. So, that means from where does this reactive power come? So, if I want to look at the reactive power requirement of the converter, see, now from where does this reactive power come? See, if you do not do any additional, if I do not provide any additional source, then the AC system itself supplies the reactive power. So, that is one option. The AC system itself supplies the reactive power. Now, invariably there are filters on the AC side to minimize the current harmonics. Now, these filters can provide reactive power at the fundamental frequency. See, if you recall, when we decided the rating of the capacitor or inductor, we saw that we took the fundamental current and the harmonic current. Now, that fundamental current is essentially supplying reactive power. Now, please note, what will be the reactive power of the inductor and capacitor. So, if I compare the reactive power absorbed by the inductor of the filter at the fundamental frequency and the reactive power generated by the capacitor of the filter at the fundamental frequency, which one is larger? Say, the inductor and capacitor will act in opposite ways. Okay. So, when it comes to reactive power, inductor by convention is absorbing, capacitor by convention is generating. Okay. Now, that is the usual convention of reactive power. So, whether generation is more than absorption or it is the other way. Sorry, absorption is more. Say, what is the expression? Take the square of the current and multiply it by reactance. Take the square of the fundamental component of the current and multiply it by reactance. So, which one is larger is the question. IF1 square into the reactance at fundamental frequency of the capacitor and IF, the same current flows, they are in series.
I think capacitor will be greater.
You think so? You are not sure?
Because capacitor is in micro, so from the omega c 10 raised to 6 will come up. So this value will be bigger.
No, without even taking the value. I mean, one need not take the value. See, look. If you look at the expression, can you not infer anything from that? Which one is? Generation is more than consumption.
Without taking value.
Yeah, why do you need value? See, we know that the value of inductor and capacitor is such that it is equal 1 by root LC is equal to the some harmonic, whether it is 11th harmonic, 13th, some harmonic, okay, which is higher than fundamental.
Yes.
So, what is happening at fundamental is the question. From that, can we not say what is happening at the fundamental? Sorry? Both should be equal at harmonic frequency. Harmonic frequency is 11th or 13th or 23rd, 25th, so on. Okay. Now, what is happening at fundamental is the question.
We know that two curves are intersecting at the harmonic, but
What is happening at fundamental? Fundamental is less than harmonic. Fundamental is always less than harmonic.
yes.
So, what is happening at fundamental? So,
As you decrease the frequency.
so there is more generation of reactive power, or more than there is net generation of reactive power or net consumption of reactive power? Net generation. So, that is what I am saying. So, AC filter is also a source of reactive power. So, the AC filters. So, without providing any additional equipment, these two or anyhow they will provide some amount of reactive power. But if it is not sufficient, say, I mean, AC filter is not actually for the purpose of providing reactive power, it is for the purpose of reducing the harmonic content in the currents on the AC side, but it also provides reactive power. So, if that is not sufficient, then the system has to provide, but it will be always at some point where the system may be overloaded. So, reactive power is supposed to be ideally generated at the place where it is required. Okay. So, that is why I mean we are familiar with this, we say power factor correction. So, all our loads are almost inductive loads. So, we do reactive power correction locally by having a reactive power generation, for say in the form of capacitor. Okay. So, shunt capacitors is another option. Any other source of reactive power? Condenser, synchronous condenser. Synchronous condenser. Any other source? You have heard of reactive power source? Any other reactive power source? Sorry? Yeah. So, if you have studied flexible AC transmission system controllers, FACT stands for flexible AC transmission systems. So, there are some FACTS controllers such as SVC, STATCOM. SVC in fact is an abbreviation. SVC stands for static var compensator. STATCOM is also an abbreviation. STATCOM stands for static synchronous compensator. So, these are the different sources. You will not get into the details of these two FACTS controllers, of course, or in general what is FACTS controllers. This is part of another course if one is interested. So, just for the sake of completeness, I am listing them. Now, there is one major difference between the last two sources and the third one. Of course, the first two are anyhow there. Okay. Now, 3, 4 and 5 are something which are additions. Now, what is the major difference between 3 and the other two, 4 and 5? Sorry? Passive. Okay. I mean, then you have to define passive active. So I didn't want to get into those definitions. Even in the context of filters, I didn't say what is. I just because somebody said active, I said passive, without even defining what is passive. No, much more simpler terms that we are familiar with. Huh? Uncontrolled. Actually, there are mechanical switches, so discrete control. There is no continuous control for shunt capacitor. It provides only discrete control. One can have many capacitors in parallel with switches. So depending on how many switches you close or how many switches you open, the amount of capacitance can change, but it takes only discrete values. That's all. If you have only one capacitor, it takes only two values. Either there is capacitance or no capacitance. But when it comes to synchronous condenser and FACS controllers, you have continuous control. Yeah, but one should know that there are some problems with synchronous condenser. So when you take a synchronous condenser, always there is a disadvantage attached with that. Synchronous condenser. First of all, what is a synchronous condenser? Motor. Yeah. So it's a synchronous machine. If I ignore losses, it is neither a motor nor a generator. If I ignore the losses, it is neither a generator nor a motor. It's just a synchronous machine which is connected to the AC grid, and on the shaft there is nothing connected, neither a load nor a prime mover. Okay, so it's just a synchronous machine. But if you just take the losses into account, one can say it's a motor. But there is no motor. Means normally you connect a mechanical load to the shaft. There is no such mechanical load. There is no prime mover as well. Okay. Now, what are the problems? I mean, there are some disadvantages due to use of synchronous condenser. Now, this disadvantage is common to all synchronous machines. See, whenever you have synchronous machine, there is a problem of loss of synchronism. See, though there is no generation of active power from this, there can be a loss of synchronism which can happen with any synchronous machine. So, one disadvantage is loss of synchronism. That's an issue. Then, I mean, this is just a possibility. Loss of synchronism is just a possibility, Yeah. Another disadvantage compared with FACS controllers. See, FACS controllers are essentially power electronic circuits. That's all. They are only power electronic circuits. FACS controllers are power electronic circuits. Now, if you compare synchronous condenser or FACS controller, I mean, by definition, synchronous condenser has a stator rotor. There is a rotating element. FACS controllers are just stationary circuits. Now, there is whenever you have a rotating element, there is a possibility of slip ring brushes, which you do have. Why? Why do you need slip ring brushes in synchronous condenser? Yeah, field has to be supplied some current, okay, or voltage, a DC voltage. Field is actually rotating. Armature is stationary. Now, how do you connect a source, DC source, to this field? So, the external DC source is some stationary equipment, and the field winding is rotating. So, to connect them, you need a slip ring brushes. So, whenever there is a contact between the rotating slip rings and the stationary brushes, there will be wear and tear. So, whenever that happens, you need to keep replacing this periodically. Of course, even otherwise, there is another location where there is a contact between stationary part and the rotating part. Where is that? Any rotating machine has a contact between stationary part and a rotating part, right? Where is that? Where do you see that contact? Or there is no contact, it is just rotating in air. That's also possible. Bearings. It is bearings. See, if you look at any rotating machine, a cylindrical structure, the two end plates, there are two bearings on both sides. Okay, so that is the contact. Of course, there are some developments. If one uses magnetic bearings, you can avoid that also. Okay, so one can use a magnetic bearing to see that it just rotates in air without any contact. Okay, but this is something which requires frequent maintenance. maintenance due to brushes, maintenance, okay, I would say maintenance of brushes, the carbon brushes that keeps wearing out, so you need to replace that periodically. So I presume you are all familiar with synchronous condenser. You see, it's just as I said, a synchronous machine without a prime mover, without a mechanical load, and it's connected to the grid. So I can generate reactive power by controlling the field current. In fact, I can even absorb, I can generate or absorb, okay, depend by varying the field current. Okay, so that's the advantage of synchronous condenser. It has a continuous control. So that's about the reactive power requirement.